today with us. Sylvain is someone I know for a while, 2003. He's been working on galactic winds, AGN winds on galaxies, the link between AGN and the host galaxies, and several aspects of them. A multi-wavelength from X-rays all the way to radio, optical, of course, infrared. And his colleagues in the group are also building instruments, as far as I know. So he has a very global view of the topic. He has some reference papers on the subject. Last year, he published a very complete, very thorough work revising the field. This is something I call the book of outflows, but it's really a very complete work that you could see. If you're starting now, it will educate you on pretty much every aspect you need to know. Sylvain is, on the official stuff, the formal stuff, he's a professor at the University of Maryland. He's been there since the 90s. Previously, his PhD, he obtained it from Lick Observatory, where he worked under the supervision of Donald Osterbrock. Well, most people here have read, I guess, his book on AGN, on diagnostics of gas. What else is there to say, Sylvain, I guess? Besides that, I was looking forward to hearing your talk on winds. I don't have much more to add, unless I've missed something out. Please do correct me. But we are very happy to have you with us today.
Okay, thank you, Calliope. I wish I was in Athens, but it's a good compromise. Hopefully that we can at least meet online like this, and I can talk a little bit about galactic winds. The idea here is that galaxies are not isolated island universes, and they're just giant ecosystem where gas flows in and out of these systems, or they're transforming to stars. And the one key question that my group and I have been trying to address is, what is the impact of these galactic winds on the evolution of galaxies, but also on the evolution of the environment, the surrounding. And this picture that is shown here tries to illustrate that. These galactic winds are highly multi-phase, as shown in this panel here. There also extends over a broad range of scales, from the very nuclear scale to the nuclear stellar cluster scale, to the accretion disk scale in the case of supermassive black hole, so sub-parsec scale, all the way to galaxy scale, or even circumgalactic scale, shown on the right here. This is 300 kiloparsecs. Obviously, this talk will not be able to cover all that, and so I'm just going to discuss the highlight of these galactic winds, but especially the cool side of galactic winds, the cool phase of galactic winds. But for those of you who are interested in knowing a bit more, getting more detail, we wrote this review that is shown at the bottom of this slide here in last year in the ANA reviews, and with Roberto Maiolino, Alberto Bellato, and Susan Alto. I invite you to look at this review if you're interested in knowing more about the physics, more about the statistics of this phenomena. But this has become one of the hottest topics in extragalactic astronomy. I'll try to explain that in this talk. So the plan today, I'll just give you some motivation. The reason why this topic has become such a hot topic in extragalactic astronomy. I'll talk a little bit about basic physics, how it works, how galactic winds are triggered, etc. Most of my time will be to spend on discussing the results on cool outflows. Because of time constraint, I'm mostly going to focus on the outflows that are best studied, the nearby ones, not so much the high redshift one, even though this topic is quickly expanding at high redshift as well, thanks to new facilities like ALMA. And then I'll say a few words about open issues and then future prospect. So motivation. So maybe the best place to start is with a movie. And so this is one of many state-of-the-art simulations of the dynamic universe, and try to illustrate the fact that these galactic winds, the so-called feedback processes, is really important to explain the universe as we see it today. So this is an example of a movie from the Illustrious collaboration. And so on the left is the dark matter distribution as a function of redshift. It started at redshift 11, which corresponds to the first star, the first seed black holes. And on the right is the gas temperature, where blue is cold, green is intermediate warm, and then red is hot. And so on the left, you can see that starting with the initial fluctuation from inflation epoch, the dark matter is growing through just gravitational collapse, and the structures are growing. And on the right, now we're starting to see different colors. And so there, the change in temperature is due to energy input from either stars or accretion onto supermassive black holes, which re-inject material and energy and momentum and radiation in the environment. And so what is already pretty dramatic on the right is the fact that it's all started pretty quietly, but as more and more energy is injected into the gas from supernova and from supermassive black hole AGN, it's dramatically changing the structure, but perhaps more importantly, it's ejecting some material outside of the galaxy themselves and redistributing on scales that are comparable to the circumgalactic medium and even the intergalactic medium. So what is not shown here on the right is the density. So this is just showing you where the temperature distribution. And you can see that between the structure, it's mostly red, so it's mostly hot material. And so it's expected to be of the order of 10 to the 5, 10 to the 6, perhaps 10 to the 7 in some cases, sort of temperature. It's a bit hard to detect. It's very diffuse, very tenuous, and it's sort of a temperature which doesn't radiate very well. And so it's actually quite hard to detect. So but that's the predictions of these models. We're now already at redshift 0. And in the end, you can see that the gas is sort of volume filling, while the dark matter on the left results into a sort of a supercluster or large cluster of dark matter. So basically the expectation is the gas will be volume filling and filling up everything in between. But the density will fluctuate. Most of the density will be close to the galaxy, and then it will fade away as you go further out. And I just wanted to emphasize the fact that this results is not depending on numerical simulation. The one I showed you was Illustrious, the one on upper left. But other well-known simulations from FIRE and EAGLE and others all have the same sort of predictions that this is a very dynamic universe, and to really be able to explain the universe as we see it now, it has to be that there's going to be quite a bit influence from galactic winds that redistribute the material on larger scale. It also prevents stars from forming. So, one key observation that dates back to many years is the fact that star formation efficiency, so in other words, what fraction of the baryon is transforming to stars, is quite a bit less than 1. Now, globally, it's a bit less than 0.1, but that number depends on the galaxy we look at. So this plot is star formation efficiency, or some measure of star formation efficiency versus the mass of the halo, the dark matter halo. And the Milky Way is at this particular location. But the point is this star formation efficiency peaks around where the Milky Way is smaller for dwarf galaxy. And we think that's due to, at least that's what the numerical simulation suggests, that it's due to the stellar effects, galactic winds that are driven by input of energy from stars, supernova, etc. While it's also smaller at higher mass. And we think that it's not due to stars. Stars doesn't contribute as much, enough energy to explain this. And so AGN, quasar, radio galaxies are the main contributor to the lack of massive galaxy at range of above 10 to the 12, 10 to the 13, or even cluster scale, 10 to the 14. So the fact that is energy injection from AGN avoids the overproduction of massive galaxies. So that's one explanation. There are possibly other explanations, but the most simulation, nearly all simulations, suggest that you need both feedback, energy injection from star, energy injection from AGN and quasar. And then we also see gas on large scale, in the local universe, but also at high redshift. Galaxies are not just isolated universes. They're surrounded by a halo of gas and dust, and they're ubiquitous. They're everywhere. They're large, 100 kiloparsec scale or more. They're metal enriched, and they're dusty also. We know there's dust in these halo. And in fact, if one adds up all the metals in these gaseous halo, the so-called circumgalactic medium, there may be more metals and dust in the circumgalactic medium than in the galaxies themselves. So, and galactic winds is one way to redistribute the metals outside of the galaxies. There's other ways. Accretion is also probably a contributor, but outflows are definitely contributing to having these circumgalactic medium, metal-enriched, dusty halos around galaxies. And that's seen at, as I mentioned, at both at nearby universe and high redshift, even redshift 3, perhaps even 5 or 6, we see these halos. So it takes place pretty quickly. It has to be a phenomenon, a process that takes place early in the universe. And these outflows I mentioned, galactic winds is one way, and that's at least qualitatively is consistent with what the simulations say. The details of a prediction of a simulation versus the observation is still not perfect, and clearly, the simulations needs more observation to constrain the exact ingredients of how you incorporate this galactic winds physics. So let me say a few words about basic physics. There's a lot more about the basic physics in the review that I mentioned at the beginning of on the first slide, but just to give you a flavor of how these galactic winds we think are triggered, basically it's energy injection or momentum or radiation that drive these winds. And in sort of the simplest case, you have that supernova remnants thermalize, or galactic winds from AGN thermalize into a hot bubble at the center of a galaxy. And that hot bubble is overpressured. And so it expands, overpressure with respect to the ISM, the local ISM. So it expands through the ISM. And so that expression is just a Sadoff-Taylor self-similar solution for a point explosion. But then in a galaxy that may have some sort of geometry like a disk, that is the one that is shown here, at some point, if there's enough energy in the bubble, it will expand and it'll start feeling the pressure gradient. And so it'll expand faster along the path of least resistance. And material that is entrained in this bubble will become really Taylor unstable. It'll fragment and it will be accelerated through that bubble. And that's basically what we see here. So this is, you have energy at the base of the disk of the galaxy and expand, and then it produced a wind or a bubble that is perpendicular to the plane of the disk, along the path of least resistance. And that's basically what we see also in an atomic bomb, where you have a stratified atmosphere. In fact, the expression, the mathematical expression, are very similar in the case of an energy conserving bubble. And then what you expect also in the simplest case is you would have those vortex, blowout vortex in a stratified atmosphere, as you see in the atomic bomb. We don't often see that in a galaxy, but in this particular object, which is one of my favorite in 1990s, we actually see this blowout vortex. So very similar physics going on. So a bit more detail, the expression, the equation of motion of these fragments that are entrained in the outflow, there's quite a few forces that will contribute to the acceleration of these fragments. One can think of the thermal pressure, but there are cosmic rays also that more and more we think are important in some cases that will help provide a force to accelerate the fragments. In some cases where radio jets are clearly seen or radio bubbles are clearly seen, that will also contribute to accelerate the fragments. Radiation pressure is most likely quite important, especially for quasar, AGN that are radiatively efficient. And it scales with luminosity divided by the speed of light. And then the term in front depends on how optically thick the material is. And to be efficient, it's better to be able to absorb this radiation. And so optical thickness is important. Higher optical thickness goes up, then radiation pressure also goes up. I'll come back to this point a bit later and explain some of these terms here. And then of course it's against gravity. And so the difference between those forces and gravity will tell us if the outflowing shell is accelerating and how far it's going to go, what sort of velocity it's going to acquire. So in the case, there's two forms of energy source, the starburst stellar processes. In the simplest case of energy adiabatic case, where the supernova remnants thermalize into a hot bubble, the expression is shown here is, it's going to create a pressure. It will be overpressured. And the pressure of that bubble is given by basically star formation rate divided by sort of the area over which it's injected, the energy is injected. So r squared, the radius of the injection zone. So I'll come back to that expression. So in the end, the key parameter for a starburst is the star formation rate per unit area. Now, how much energy is injected and over what sort of area, so that you have a bigger piston to accelerate the fragments. And for quasar, there are many factors. There's cosmic ray, there's jets. But if one just look at the radiation, there's also the thermal pressure. But if one looks at only the radiation, what's remarkable about quasars is that if you assume some sort of radiative efficiency, so to build a black hole of 10 to the 8 solar masses, which would be typical for a large galaxy. If you assume a 10% efficiency, which is also not unreasonable, then you get an energy radiated over the lifetime of that black hole, of that AGN, of 10 to 61 ergs, which is a lot more than the binding energy of the galaxy, even this large galaxy. It's 1-2 orders of magnitude larger. So, if that energy, this radiative energy, was captured by the ISM of the galaxy, it would just blow it away pretty easily. So that's why I say here, it's potentially lethal to a galaxy. And the same argument applies even to our own Milky Way galaxy, which has a black hole mass of 10 to 6, but the binding energy is also smaller. So, surprisingly, we're here, which is a good thing. And so clearly that radiative energy was not captured by the ISM. It leaked through, and most of it leaked through out of our galaxy. But the point is that there's plenty of energy that is produced from the quasar, just looking at the radiation, to have an impact on the host galaxy. So in principle, it's actually pretty easy for quasar to have an impact on their host galaxy. Okay, so let me show you some results, and I'm going to start with starbursts, sort of more benign, more classic starbursts, and go to the more powerful system. So, the first object, that sort of a classic object, is M82, the nearest starburst galaxy in the northern hemisphere. And the classic picture is shown here in H alpha. So in white is the stellar disk, the galaxy itself, where the stars are. And then in red is the warm ionized gas traced by H alpha. And then on the right, you have the ionized gas, but different phase, 10 to 6, 10 to 7 degrees, X-ray bright from Chandra data. So that's sort of classical picture where the starburst in the middle injected energy and drove a wind that leaked through the path of least resistance on scale of, in this case, 3 to 4 kiloparsecs from the center. Although we know that the X-ray actually extend even further, up to 11 kiloparsec. But what about the cooler gas? This is just a warm ionized gas or hot ionized gas. Starting with the warm molecular gas, H2, this is from rho vibrational line. So has a temperature of 1,000 degrees or so. Follows very similar structure as the warm ionized gas, which may be a bit surprising. But what's even more surprising is that the colder molecular gas also follow a very similar structure. That's shown on the left. This is the velocity field, which is typical of rotation. But then this material here that corresponds to the cone, the northern cone, and then the southern cone, doesn't follow the rotation curve. So it's clearly entrained in the outflow. And then if one does the arithmetic, you get the mass outflow. That corresponds to 25% of the total molecular gas in this object is outflowing. So it's really substantial. It's really important to consider that. And then energetics, 10 to 55 ergs, is as much, perhaps a bit more, than the energetics in the warm ionized gas traced by H alpha. So again, that component is really important to consider. It cannot be neglected. So this is the cold gas at a few tens of degree Kelvin. So the picture that we have is that of entrainment of the material from the disk onto the halo. And at the same time, if you have the molecular gas outflowing into the halo, then the dust will follow. And that's exactly what is seen as well. That's a picture of the dust, either the warm dust or the cold dust has very similar structure where it's also entrained in the outflow. So the global picture looks a bit like that. The starburst is in the middle. So the midplane of the galaxy is here horizontally. And the energy injection is only taking place in the middle from the starburst, star formation rate of a few solar masses per year, 9 solar masses per year. And it's injecting energy, momentum, radiation into the environment. And the material from the disk is lifted up into the halo. And the hot gas traced by the X-ray appears to extend to 11 kiloparsecs, as I mentioned, and hits the clouds there and stops there. But some of it would have escaped the galaxy. But that's not the case for the cooler gas, H1, which I didn't discuss in detail at all here. But it extends on similar scales the molecular gas. It seems like the molecular gas dissociate as it is lifted up the disk into H1. But it doesn't have a velocity that is large enough for it to escape the galaxy altogether. So it either gets deposited into the circumgalactic medium, into the halo of the galaxy, or it rains back down onto the galaxy as shown in this picture in sort of a fountain. And that's often the case for the cooler gas. It reaches velocity where it's going to be deposited in the circumgalactic medium. So it will contribute to the circumgalactic medium buildup or feeding, but it's not going to escape altogether. The warm or the hot ionized gas, in some cases, may escape, however. Now, you might say this is just for M82. This is the nearest object. But if one look at another classic example of a starburst, NGC 253, which has the star formation rate surface density that is very similar to M82, so it's high enough to drive an outflow, we see structures that are very similar. The molecular gas shown in contour wraps around the outflow itself, which is shown in blue here in the soft X-ray. So the X-ray is a bit more volume filling, and the molecular gas is wrapped around and being entrained out of the galaxy up to the CGM, up to the circumgalactic medium scale. And one thing that is interesting for this particular object, this was observation with ALMA, where we can actually have quite a bit of information from multiple lines. We find that not only is the gas from the disk being entrained in the wind, has the same properties in terms of line ratio and densities, but if we make a cut of the velocity along this line, we find that it seems to have higher and higher outflow velocity as it goes further from the disk, as if perhaps these clouds are being accelerated. So what's remarkable, and that comes back when I talk about open issues, is the fact that somehow nature has found a way to accelerate these clouds that are 10 to the 4, 10 to the 5 particle per cubic centimeter at velocity, in the case of 253, a few hundred kilometers per second. But we'll see that for other objects, the velocity can be up to 1,000 kilometers per second. And that's actually very hard. They're like bullets being accelerated at high velocity on scales of hundreds of parsecs, or in some cases, kiloparsecs. So that's a theory or numerical simulation that have not completely explained that observation. But it's clearly the case. It's seen in M82, it's seen in NGC 253, and it's seen in many other objects that I'll discuss later. Now you might say, okay, this is for starbursts. You have high star formation rate, surface density. So you do expect these winds to take place and entrain the cool gas. Well, it turns out that, as expected from theory, if you reduce the gravity, so instead of doing in semi-normal galaxy, you use a dwarf galaxy, well, you also have these dusty winds. And that's one example here of a dwarf galaxy, where the star formation rate density is much less than 1. In fact, it's 0.04. And so the pressure is lower, but the pressure of the ISM is also lower because it's a dwarf galaxy. And when we look at the dust, it extends well beyond the stellar distribution. And in fact, 50% of all the dust that we detect is outside of the stellar disk. And there's other signs that that's due to the fact that there are galactic winds. We can see bubbles, even the dust itself, we see bubble and filaments that are also seen to some extent in H alpha as well. So the galactic winds are clearly important in driving dust outside of galaxies, even in dwarf galaxies. But that's not unexpected, because the gravity term is lower in these galaxies. And so you don't need as much energy input to drive these winds and drive the dust and the cool gas outside of the galaxy. Now, the other thing that we could do is, instead of having stars, energy from starbursts, we can put a quasar, an AGN. And I'll just mention one object, arguably my favorite object. That's the nearest quasar, called Markarian 231. And these winds are seen basically on all scale. And starting on the left, this is how it looks like optically with an image of HST, the quasar in the middle, and the host galaxy, which is the results of a merger. You see, is a bit disturbed morphology. But if we look at it in the middle with UV spectroscopy and even X-ray spectroscopy, one see the signature of fast winds, these X-ray or UV winds, which will may have a role in driving the winds on larger scale. But these winds, so that's the nuclear scale, subparsec scale. But these winds extend on galaxy scale. And that's shown, for instance, in this panel, which is on scales of 3 plus or minus 3 kiloparsecs. So it's over that area here after rotation. And what is shown here is the neutral gas, the traced by sodium as velocity. This is all done in absorption. So we know that it's blue shifted and it's moving in our direction. So it's in the form of a cone in our direction at velocity of 1,000 kilometers per second. That's seen in using that tracer of sodium. It's also seen in H1, the 21 centimeter in absorption. There's this extended blue wing out to 1,500 kilometers per second. But even more remarkably is that outflow is detected in molecular gas. OH was this bluing, absorption bluing, like a Piscini profile, signature of an outflow, again, extending on 1,500 kilometers per second. That was detected with Herschel Space Observatory. It's also been mapped now with interferometer, millimeter wave interferometer to look for the CO velocity field. And we see again the signature of outflows on the scales of 1,000 kilometers per second and on scales of kiloparsecs in this object. So this is one of many objects where the lesson learned from studying these objects at redshift 0 is that the cool gas, either traced by sodium or H1, or the cold gas traced by OH and CO, show that that phase of the outflow is energetically dominant in gas-rich system. This Mark 31 is a gas-rich quasar. And the central panel here, just to illustrate the big picture, this is the HST image here. This HST image covers this area. And this is to emphasize that it lives in a much larger halo, the circumgalactic medium seen in the X-ray. And we think that part of this circumgalactic medium has been fed by the winds that takes place on kiloparsec scale or so, because the velocity is large enough, or previous episodes of these outflow have fed the circumgalactic medium, because we know about the abundance, the oxygen versus iron, etc. And we know it's been enriched in alpha elements that suggest that they have gone through star formation and have been ejected out of the galaxy into the circumgalactic medium. So one always have to take into account or remember that whatever we see at a particular wavelength, like the optical wavelength, doesn't fully tell us the picture of the entire galaxy and its environment. So we think these winds are feeding the CGM. So this is just one object, but after many years of work by our group, but also many other groups, and Calliope has been part of this effort as well, we know that at least in the local universe and among gas-rich system, either starburst or quasar, that a large fraction of these gas-rich actively star-forming or AGN, 70% have these molecular winds. And the outflows, broad range of outflow velocity, but in terms of maximum outflow velocity is of order 1,000 kilometers per second. And the median is 500 kilometers per second. So these have high enough velocity that the material will be deposited into the circumgalactic medium. So they will contribute to feeding, what I call feeding the circumgalactic medium, keeping it active. Because if you stop feeding it, the material will just rain back down and form stars in the galaxy. And so you need replenishment. And we think these outflow could contribute to that. In terms of energetics, the scales range from fraction of a kiloparsecs to up to 10 kiloparsecs. In fact, if we look at the neutral gas, recent results at nearby redshift, 0.5 or so redshift, the neutral gas sometimes extends to 20 kiloparsecs or perhaps even larger. It's just a matter of sensitivity of our instrument, we think. The 10 kiloparsecs was done with ALMA, but it was sort of a snapshot with ALMA. If we to detect the Milky gas. If we go deeper, it'll probably extend further. Energetics, mass outflow rates can be quite large. So it means that the material gets ejected very quickly, runs out of gas, and star formation will be stopped. It'll be quenched. The momentum rate compared with the radiation pressure can be quite large. So we think that in the most extreme case, one cannot only do it radiation. I'll come back to that in a moment, but there's plenty of energetics from just the bolometric luminosity, and that could be the starburst or the AGN, only 2% or less that is captured to drive these outflow. So this is shown in this plot, which is the dPdt, which is this term here, versus radiation pressure. So some of the objects are of order 1. So perhaps these objects can be driven by radiation pressure, but these objects that are more extreme reach values of 10 to 20 more than the radiation pressure. So they are harder to explain by momentum-driven radiation pressure. But again, there's plenty of energy overall to drive them through, just as long as energy is driven. Now, I wanted to emphasize that it doesn't really matter if it's a starburst or an AGN that drives these winds. They seem to both contribute to these winds. They work together in driving these winds. Notice the expression here is bolometric luminosity. So that's the starburst luminosity and the quasar luminosity together. If one looks only at the AGN luminosity versus the outflow velocity, you already have a very nice correlation. As you increase the AGN power, the outflow velocity increases, but there are a few cases which do not follow, as in this particular object here that we had found in 2016. But it turns out that object has a pretty compact, actively star-forming population. And so it's driving energy, it's driving the outflow thanks to the star formation rate and the surface density of star formation rate. So the two are contributing together. And a lot of effort was invested in finding if it's an AGN or a starburst driving these outflow. But in the end, it seems like it doesn't really matter. Both of them are contributing when they're present. But to get the most extreme cases of velocity and momentum and energy, you need to crank up the luminosity of the AGN or crank up the star formation rate very high. But in the most extreme case, all of these objects have a very powerful AGN. Quasar, really. So let me just say a few words about open issues. I'll just mention two of them. The first one I mentioned was this dPdt versus the radiation pressure. I call that the momentum boost. When it reaches value of 20, it's starting to be a bit hard to explain. In the first scenario, hoping there was radiation pressure, and there's been a lot of work that has been done into the cases where you have a galaxy that's covered in obscured material, 4pi coverage. And so the radiation gets trapped into that cocoon of dust, and you get multiple scattering and trapping of the infrared radiation, even the far infrared, if the tau is large enough. In that case, this radiation term, so this term becomes negligible because tau of UV is very large, and then tau of IR can be larger than 1. And this term, there's fudge factor that depends on basically what the physics is, numerical simulation, suggests that this term, eta times tau IR in the most dusty cocoon could be larger than 1. So you can get a boost of more than 1 times L bol plus C. So you might get a factor of 2, 3, maybe 4. But in the end, numerical simulation so far suggests that having a factor of 20 is hard. And so one has to comes to the second scenario, which is basically energy conserving outflow where you have an inner wind driven by the AGN, for instance, in the most extreme cases, because all these objects here at 20 have quasars in them. And so it seems like there's a relation. In the most extreme case, you need a quasar to drive these outflow. And we do see X-ray winds, we do see UV winds in many of these systems, like in Markov 231 I mentioned earlier. And so this inner wind, which is often just radiation driven, will impact the ISM on slightly larger scale and heat it up and produce a hot equivalent of a hot bubble, which is sort of adiabatic hot bubble, very high temperature. The shocked wind will be 10 to 10 degrees. The shocked ISM can be 10 to 7, 10 to 8 degrees. So it's pretty hot and it doesn't radiate very well, very efficiently. And so it's the equivalent of a hot bubble. So it's the case of very energy driven outflow. If you just look at conservation of energy, you can get a dP/dt that is quite a bit larger than L/C, depending on the detail of what is the velocity of the inner wind versus the velocity of the outer wind. And then there's going to be an efficiency F here, which can be 0.5, 0.3. That's the fraction of the kinetic energy in the inner wind that goes into driving the bulk motion of the outer material. But certainly it's possible to get, in this situation, a boost, a momentum boost that reaches value of 10 or 20. So I would say that currently, to get those most extreme number, scenario 2 is favor over scenario 1, although scenario 1 probably applies to most of the systems that are not as extreme as that. The second open issue that I wanted to mention was how does nature drive these molecular winds, especially the extreme molecular winds, where we see velocity of 1,000 kilometers per second on scales of a kiloparsec, like in Markov 31, that's what we see. If one compares with numerical simulation of individual clouds as one of, there's a number of references here. This figure is from Schneider and Robinson, but basically all these other papers agree with the conclusion that it's actually very hard to drive a cloud by a hot wind. There's erosive forces that destroys the cloud, as shown in this simulation. And so in the end, the clouds does not reach high enough velocity or does not reach a large enough distance to be observed as cool gas and as we observe it in these galaxies. There's been a number of parameters here. One of them more recently has been tried to include magnetic fields to protect the clouds against these erosive forces. So that's magnetic draping. And it does help to help the clouds survive to larger distances and higher velocity, but still not able to reach to simulate a cloud that has a velocity of 1,000 kilometers per second out to a kiloparsec. So one other possibility to explain these molecular winds on that sort of scale and that sort of velocity is that perhaps the highly ionized material that came from the interaction of the inner wind to the outer with the ISM becomes highly ionized and it just accelerate in the form of this hot bubble. But eventually the hot bubble material or the shocked ISM becomes thoroughly unstable and it forms clumps. And eventually these clumps gets dense enough that it reaches a temperature that is now visible in as neutral material or even molecular gas. So that's the second scenario where thermal instability in the hot wind or in the mix between the hot wind and the cool material, so the warm mix, maybe the trigger for in situ formation of the clouds. And in that case, the clouds are naturally have the same velocity of the wind because they came from it. And that, again, there's been a number of papers that have described that, and the one that I've shown here is from Richings and Fauché-Giguère a few years ago. The big question for this sort of models is whether or not dust survive the initial shock of the inner wind onto the ISM. And if it doesn't survive, it gets destroyed in this initial shock. Remember, the temperature of the shocked wind is 10 to 10 degrees, and the shock ISM is 10 million degrees or more. And so it's not trivial to know if the dust survived that initial shock. But if it does, then you can form the molecular gas on the right time scale to be observed on scales of a few hundreds of parsecs, as we see it from Herschel and interferometries, millimeter wave interferometry. But if the dust doesn't survive, then obviously it would not be able to form the molecular gas. So the dust as a catalyst to form the molecules. And so if the dust doesn't survive, then that scenario would have a hard time explaining the molecular gas on hundreds of parsec scale. Okay, so let me talk about future prospect very quickly. Like many of us, we're waiting for James Webb Space Telescope. This is a 6.5 meter telescope in space that will be launched hopefully on Halloween, October 31st, 2021. We all hope that's without further delay. And we have early release science program that is led by Dominika Wilichalek as the PI, and Nadia Zamkowska, myself, and Dave Repke are co-PI or important contributor to that project of imaging, basically doing spectroscopy on quasars, on 3 quasar, nearby one, intermediate redshift and high redshift, to see what can be done with JWST. We think that the spatial resolution and 3D aspect of the James Webb Space Telescope, it will be ideal to study these cool outflows in quasar. So stay tuned, right? So let me just summarize. I think I'm basically out of time. So cool winds in galaxies ubiquitous, especially in gas-rich system. I didn't discuss the high redshift universe, but it certainly appears to be the case that these gas-rich or cool winds are frequently observed in starburst galaxy at high redshift and nearby universe, and also in quasar, in the dusty quasars, in the infrared bright quasar, they're ubiquitous. Although the statistics at high redshift, beyond redshift 2, is still patchy. At least in the local universe, this is a sort of velocity, and we think that they're contributing to the CGM. At higher redshift, the velocity are similar, but their mass is smaller, and so it may very well be that some of this material escape the galaxy altogether. But at least in the local redshift, they seem that they contribute to feeding the CGM. The cool material doesn't escape altogether. The energetics are such that in the most extreme case, you need a quasar to drive these outflows. And there's plenty of energy, even just radiative energy, to drive these outflows. So there's no energy problem. The open issues that remains is, how does nature accelerate these clouds? If we're really talking about accelerating the clouds, it's not clear that they can survive for this long and reach the velocity that we observe. Perhaps the alternative solution is that the clouds form in situ, where they form out of the shocked, warm, or hot material, as long as the dust is able to survive that initial shock. And again, as I mentioned, the prospects are excellent in the future. JWST and other facilities, ALMA will continue to contribute to that research. It's been very productive, but JWST will provide another window to provide excellent angular resolution and also 3D spectroscopy of the entire outflow for outflow not only nearby, but also at a higher redshift. And so it looks very promising. Cross our fingers for JWST will be launched in a few months from today. And so that's it. So if you want to know more detail about the physics, more detail also about the statistics and the properties of these outflow and the open issues, I invite you to have a look at this review that we wrote last year in A&A Review. And I'll stop here.
Thank you very much for that. Yes, you were on time as well, perfectly on time. Thanks for this nice overview. So, Calliope, would you like to?
Yes, I do
Yeah.
have a question myself, but
Yeah, I
I'm
suppose.
wondering if other people. I can't see the chat right now. Let me have a look. Until somebody takes their time to think their own question, I would like to ask the following. On your DPDT, you mentioned the force by cosmic rays, but you didn't come back to that at all. And at least in jets, that would be pretty important. We start to see that modeling. But I was wondering also the role of cosmic rays in any other wind, not jet-driven wind, I mean, because you may have a local amplification. So I was wondering, of your view on that.
Yeah, I did skip one of the slides. So as you know, I mean, for the jet, there's clearly an impact from that I did not discuss. It can be acceleration, but it can also adding turbulence to the environment, which will also impact the star formation. But it turns out that some of the numerical simulation recently show that even for the Milky Way, just trying to explain the circumgalactic medium in our own galaxy may have an impact. The cosmic ray may have an impact. And so obviously it's a lot more difficult to model it also. But it seems like, the numerical simulations are really catching up. And in general, if you include cosmic ray just at the level of, let's say, 10% of the energy, thermal energy from supernova, which is a reasonable approximation, they already have an impact in terms of just adding energy to the outflow, making them denser, less structure, more extended. But I could show a slide of that. Maybe I can stop sharing just for a second. So this is just a case, not even jet, but just general effect of cosmic ray on from star formation. Okay, let me share again. So this is just the Milky Way, right? The upper panel is, supernova only, and then the lower panel is with cosmic ray. Just looking at the morphology is quite different. It's smoother. The outflows are denser, colder, and slower. And so more and more, it seems like it's important to include them. And that's just for starbursts, right? For AGN, especially if it's directed, then it'll become even more important. But I think, the difficulty is modeling. I know there's quite a bit of expertise in Athens University that about on cosmic rays and high energy processes. And there's actually also quite a bit of expertise at Maryland too, but it's difficult to go from light year scale to kiloparsec scale. A lot of assumption has to be put in, but certainly the current, this is 2018, was also 2020 simulations that basically confirm that.
Just to give you a preview of some results I've been working, because that's why I asked about the starburst. So we're studying the excitation of the molecular gas in jet-driven winds. And in these models, we do include cosmic ray heating. Imagine an equivalent of cloud with cosmic rays. Well, in fact, some cloud models do include cosmic rays. Something else, not cloudy, but something similar. So CO excitation and other molecules. And we find that the heating can come either from shocks or from cosmic. Both are viable with the CO sled and the HCO plus sled. And so it could be either or, with a very normal increase, like realistic increase in the cosmic ray flux, like 2 or 3 orders of magnitude between the regular SN and jet impacted regions. So it can do everything. So that's why I was wondering whether, you know, in any other EGNs, they play more of a role that people think, and the momentum boosting doesn't need to be as high. That was the point.
Mm-hmm. Yeah, it's a big factor. So I don't know if it will, factor 2, I wouldn't be surprised. Factor 5 is, I think, is a bit of a stretch, but I can be proven otherwise. Certainly, ionization is seen, like in Marking 31, as you know, cosmic ray ionization on the Mocha gas has been demonstrated by one of the paper by Gonzalez Alfonso that I'm on.
Oh yes.
So I think that happens in some objects, but that's just the ionization. But then from that, we could perhaps estimate how much it's contributing in the form of momentum and pressure. Yeah.
That's right. Somebody else who may have a question?
I have a question. Yes. Maybe it's naive, but you said that 2 of the open questions are related to the physics and the acceleration of these clouds, for instance, and you proposed or you presented alternative scenarios. I was wondering if it is going to be possible with the program that you are going to lead, like with the James Webb Telescope, how you're going to resolve these questions. I mean, what are the signatures that you are looking for to distinguish between the in situ formation and the acceleration?
Yeah, no, that's a very good question. So on the nearest scale, we'll be close to that scale where we can actually resolve, GMC clouds, but only for the very nearest one. So it will apply maybe to M82, NGC 253, the nearest starburst, but it won't apply to the more distant system, the quasar-driven system. However, in this scenario where it's in situ, these models, for instance, the Richings and Fauché-Giguère paper, make some predictions on line ratios. So they daringly predicted that the H2 that is visible from JWST, not the near infrared one, but the mid infrared one, would be quite a bit stronger. A large fraction of the total energy output in the Mocha gas would be produced in these H2 that is visible from JWST. So they made those predictions in 2018, which is pretty daring. But that would be, we'll be able to test that if that's indeed the case. And then there'll be some spatial information, like in the nearest system, where you can actually compare in detail what they predicted in this model with what we're able to see. So spatial information will be useful as well. Because where the Mocha gas is tells us about, okay, how much time did it take to go from fully ionized wind to Mocha gas? And that's a prediction of the model, and how much of that energy is emitted in the lines. That's another prediction.
Okay.
Actually, Sylvain, please let me follow up on that one, because I didn't quite get it. I mean, I didn't get the assumptions behind that. How is the intensity of the H2? Or, I mean,
their model assumed that dust completely survived the initial impact of the inner wind onto the ISM.
Okay.
And so, and one can argue either way. I'm on the fence actually about that, because if you look at supernova remnants, like supernova 1987A, it seemed like dust while it formed, or in other cases, dust seems to be able to find a way to survive these shocks from supernova, which is not too different in velocity than these here. But in any case, so they assume that dust survive. So basically the dust to gas ratio was constant everywhere. At beginning, the gas is ionized, but the dust is still the same. And then through thermal instability, then you form the molecular gas thanks to the dust. So that's their biggest assumption in their model. And so if that's not the case, and it takes more time for the molecular gas to form, then thanks to spatial information, we might be able to see that there'll be a gap between the very inner region and where the molecular gas, the H2 is formed or is produced, emitted from JWST.
Separate between what has been, some will be produced, sure. I mean, some fraction of the dust realistically will be destroyed, some will survive, some will be produced. How do you separate it from what has been just dissipated from clouds that are bound in place? And how do you distinguish in situ creation from just dismantling, let's say, clouds?
Yeah, I think if it's in between, we're not going to be able to tell. I mean, we're just going to say it's in between. If it doesn't survive, then we'll see a gap. And then now in NGC 253, the starburst, we think actually we see clouds being accelerated. I mean, that's one possible explanation of where we see the velocity increasing as it goes further and further, this 1 kilometer per second per parsec. There's other explanation, but certainly one explanation is the clouds is able to survive. Nature has found a way to accelerate these clouds on scale of hundreds of parsec and velocity of hundreds of kilometer per second. Of course, this is different than the more extreme cases.
Somebody else may have something for Sylvain. Sorry, I might have missed it. How many objects are you going to look at?
So the ERS, it's a small program. So it's 3 objects. One is at redshift 0.4, another one is at redshift 1.5, and another one at 2.9. And that's sort of by design to see, the nearest one will be easy. The intermediate one should be feasible, and the more distant one will be a challenge, just to see what JWST can do. But they all have signatures outflows already. So it's not a question of proving that they have outflow, but just to prove the concept that it can be done on these bright quasars.
Sense. Anyone else? Maria, you typed something?
Yes, I typed about, there is one interesting Seifert galaxy actually, interesting in terms of neutrino production, which might be NGC, yes, NGC 1068. It is at a distance of 14 megaparsecs, and I was wondering if this is, I mean, it should be within the capabilities of James W. Webb, right?
Oh, it's on one of the GTO targets.
Ah, it is. Okay.
Yeah, so it's
sorry, I missed that.
It's going to be observed. Yeah.
Okay.
And there's a lot of data on ALMA from ALMA. Of course, the energy, it's not a very powerful outflow. It's present, but it's not quite quasar-like outflow. So it's going to test the lower luminosity sort of range of outflow.
Yeah, okay, that would be cool, because there are some models invoking shocks of winds from NGC 1068 with the ISM in order to accelerate particles. And to be honest, I don't remember what are the energetic requirements for the winds, but yeah, it would be, I think it will be very nice to revisit
Oh,
these
it
values.
will be a very nice object. Yeah, no, it's one of the top of the list for the GTO targets. So there'll be a very nice. We have to wait a year or so because the GTO targets, the data don't become readily available, but certainly within a year or two, the data will be published.
Okay.
People have been silent today, but I realized that we have still exams going on. That's why we had some people were at the exams. So we have, sorry about that. We have a little bit smaller participation than usual, but it so happened that there was an exam right now. And that's the reason why it's happened. So if nobody else has a question, that's the time to ask. Otherwise, let's thank Sylvain for being here with us today and giving us this nice talk. And we'll be looking forward to having you here again at some point.
Yes, in person.
Yes, yes.
Forward to come back to Athens and enjoy what Athens has to offer. It's very nice.
That's right. It would be nice to have you indeed. Okay, well, thanks again, Sylvain.
Thank you very much.
Okay. Talk to
Bye.
you later.
Bye.
Bye. Thanks a lot.
Thank you.